I feel like we tend to think of truth as this absolute thing.
Right, like a binary.
Yeah, exactly. Like you either have a disease or you don't. Or the email in your inbox is either a malicious phishing scam or it's just a legitimate message from your boss.
Right. It feels like it should be entirely black and white.
Yeah, we really crave that kind of certainty.
Oh, absolutely. We expect this clear, definitive line separating one reality from another, especially when the stakes are really high. It's honestly the absolute definition of a foundational concept just hiding in plain sight. I mean, it is the visual map of how we measure accuracy across nearly every scientific and technological field today.
Okay, let's unpack this. Because, receiver operating characteristic sounds like a dense chapter in some vintage ham radio manual, right?
Yeah, it definitely does.
It does not sound like the mathematical engine powering like Silicon Valley data science or modern oncology.
No, it doesn't. But to understand why we rely on this specific statistical graph today, we really have to look at why it was invented in the first place.
Right.
And that takes us straight into a literal life or death scenario in the 1940s.
Which is such a wild pivot. So take us back there.
So the historical context here sets up the entire philosophy of the math. Following the attack on Pearl Harbor in 1941, the U.S. military realized they had this massive fatal vulnerability.
Right, with incoming attacks.
Exactly. They desperately needed to better distinguish Japanese aircraft using radar. But early radar wasn't, a clean video game screen with little red triangles pointing out the bad guys.
It was incredibly messy.
Very. The signals bouncing back from a target to a receiver station were often of very low energy compared to the noise floor of the ocean and the atmosphere.
So it's just a barrage of fuzzy blips, static ambient noise.
Yeah, exactly.
Yeah.
So electrical engineers and radar technicians had to figure out a way to measure a human operator's ability to make these vital distinctions under immense pressure.
Because they had to ask, is that specific blip an enemy bomber, or is it just a really dense flock of birds?
Right. Or is it a battleship, or just some weird reflection off a massive wave?
Wow.
So they needed a quantifiable way to grade the operator's characteristics. Hence the name, receiver operating characteristic.
Which is an incredible origin story. But looking at our sources, this old World War II military concept somehow made the leap into becoming the gold standard in modern hospitals and machine learning.
Yeah, it did.
So what does this all mean for a doctor or a data scientist today? How did an old radar concept end up in, modern MRI machines?
Well, because at a mathematical level, spotting a bomber in the clouds and spotting a tumor in an X-ray are fundamentally the exact same problem.
Really? Just signal versus noise.
Exactly. Whether you are a radiologist or radar operator or fraud detection AI looking at credit card swipes, your job is to spot a weak signal hidden in a sea of noise.
That makes a lot of sense.
Yeah, and so in the 1950s, psychologists adopted this curve to study human perception. And then soon after, medicine brought it in to evaluate blood tests and diagnostic tools.
And today it's just everywhere.
It is the cornerstone of machine learning. The context constantly changes, but the core challenge of separating signal from noise remains identical.
Okay, so to understand how doctors or algorithms actually make these detections, we first need to look at the 4 possible outcomes of any binary choice, right?
Yes, exactly. The grid of truth.
Right. We all know the basic confusion matrix, true positives, false negatives, that standard 4-box grid.
Right. So using the medical example from the source, if you actually have the disease and the test catches it, that's a true positive.
Right, working as intended.
Exactly. And if you're completely healthy but the test says you're sick, that's a false positive, a false alarm.
And then a true negative is you're healthy, and it says you're healthy.
Yep. And the worst one, a false negative, is you have the disease but the test says you don't. It's a miss.
Okay, so I want to use an analogy drawn directly from the source to ground this, because it blew my mind.
Oh, the random guessing one.
Yeah. If you have a completely random classifier, it's exactly like flipping a balanced coin to diagnose a patient.
Yes.
Imagine a doctor just looking at you and going, heads, you need chemo. Tails, you're fine.
That's a terrifying thought.
Truly. But mathematically, if you test enough people that way, you will accidentally catch 50% of the sick people.
Right.
But you'll also falsely diagnose 50% of the healthy people.
Exactly. And that introduces the 2 vital metrics we derive from all this. You have the true positive rate, which is your sensitivity, your probability of detection.
Catching the bad thing.
Right. Versus the false positive rate, your probability of a false alarm. And balancing those 2 is the absolute heart of any decision model.
Okay, so if we plot those 2 rates, true positives and false positives, on a graph, We get the visual map of this whole thing, right? The ROC space.
Yes, let's map that space out visually for everyone. So imagine a standard graph. Your y-axis, running vertically, is your true positive rate.
So out of everyone who actually has the disease, what percentage did your test catch?
Exactly. That runs from 0 to 100%. Then your x-axis, running horizontally, is your false positive rate.
Out of everyone who is completely healthy, what percentage did you accidentally diagnose as sick?
Right, so the top left corner of that graph is the holy grail.
Right. Coordinate 0 on the x-axis, 100 on the y-axis.
Yep, that means 0 false alarms, but 100% of the sick patients caught. It's perfect classification.
But if you draw a diagonal line cutting straight from the bottom left corner to the top right corner, you've just mapped out that random coin flip we talked about.
Right. Any purely random classifier, no matter the sample size, will just hug that diagonal line. It's literally called the line of no discrimination.
Here's where it gets really interesting. I was looking at the contingency tables in the source material, showing different classifiers plotted in this space.
Oh, yeah.
And obviously, points above that diagonal line represent good results. They are performing better than random chance.
Right.
But there are points mapped below the diagonal line, which means the model is performing worse than random guessing, worse than a coin flip.
It's so counterintuitive.
Right, because at first glance, you'd throw that model in the trash. But mathematically, if a predictor is consistently wrong, you don't throw it away. You just reverse all of its predictions.
I secretly love this part of binary classification.
It's amazing. If the algorithm says the email is spam, you just send it to the inbox. If it says it's safe, you send it to spam.
Exactly. By doing the exact opposite, you flip it across the center point of the graph. You instantly turn a terrible predictor into a highly predictive, useful tool. The math completely supports that. The distance from that diagonal line in either direction is the true indicator of how much predictive power a method has.
That's just wild to me.
But, navigating the space isn't just about plotting one dot on a graph. A continuous output model, like a blood test or a machine learning probability score, gives you a sweeping curve.
Right, the actual ROC curve.
Yeah, and you navigate that curve by shifting what the source calls your threshold.
Okay, let's use the source's example of blood protein levels to explain this.
Good idea. So imagine people with a specific disease have an average blood protein level of 2 grams per deciliter, and healthy people average 1 gram per deciliter.
But those are just averages. In reality, human biology is messy.
Very messy. The populations are normally distributed, meaning their bell curves overlap. You have perfectly healthy people who naturally run a high protein level and sick people who have unusually low protein. As the doctor, you have to place a vertical line, your threshold, somewhere on that overlap. If you say anyone over 1.5 grams is officially diseased, you'll catch a lot of sick people.
But you'll also scoop up those healthy people whose levels just naturally ran a bit high.
Exactly. Those are your false alarms.
So if you want to avoid scaring healthy people, you might slide that threshold to the right. You say, we will only diagnose the disease if the level is above 1.8 grams.
Right. You drastically reduce your false positives. But the inescapable trade-off is that you increase your false negatives. You start missing sick people.
And the shape of the ROC curve basically maps out every single possible trade-off you could make between those two overlapping bell curves. Right?
Exactly. It forces you to visualize the cost of your decisions.
But human nature being what it is, we hate looking at complex, nuanced trade-offs.
Oh, we avoid it at all costs.
Right. If I'm an executive buying an AI tool, I don't want to analyze a curve. I want a single, easy-to-read grade.
And that brings us to the AUC, the area under the curve.
Right.
The AUC is arguably the most commonly cited statistic when evaluating classification models. In probabilistic terms, it's the probability that a classifier will rank a randomly chosen positive instance higher than a randomly chosen negative one.
Okay, let me push back on this because this feels like a massive pitfall.
Oh, it absolutely is.
Like, if I'm looking at a model and the vendor boasts it was an incredibly high ROC AUC, say 0.9, I'd intuitively look at that and think, that's a 90%. That is a solid A grade.
Oh.
Isn't a 0.9 essentially an A?
It sounds phenomenal, but the source material outlines several major criticisms of using AUC as a standalone metric. It's a huge trap.
Why?
Because a high AUC of 0.9 might still correspond to surprisingly low values of precision in the real world, like a precision of 0.2.
Wait, let's define precision real quick so we don't get lost.
Sure.
Precision is just asking.
Yeah.
Of all the times the alarm actually rang, how many times was there a real fire?
Exactly.
So a precision of 0.2 means 80% of your alarms are entirely false. How can the area under the curve be an A grade if the test precision is that useless?
Because of how the AUC calculates total area. It includes the entire area under the curve across every conceivable threshold.
Even the bad ones.
Yes, including regions of the curve with low sensitivity and low specificity like below zero point 0.5 that are practically useless in the real world.
It's like grading a restaurant based on its entire 20-page menu.
Hmm.
Giving it 5 stars because the caviar is world class, even though everyone only orders the pizza and the pizza's terrible.
That is a perfect analogy. What's fascinating here is that summarizing a complex trade-off into a single number inherently loses vital information about how the algorithm actually
Right.
behaves.
It bundles absolutely useless threshold data into your final grade,
Exactly. It tells you about sensitivity, but it masks the precision almost entirely.
which is pretty alarming if you're deploying a cancer screening tool based purely on an AUC score, thinking it's highly accurate.
When in reality, it's just going to flood your hospital with false alarms.
Wow. So because of these exact flaws, scientists and engineers have had to invent alternative ways to measure performance that focus on what actually matters.
Yes. The ROC curve is foundational, but it is no longer the only tool in the shed.
Let's walk through some of those alternatives mentioned in the source that fix the ROC curve's blind spots. First up is the TOC, or total operating characteristic.
Right. So the primary flaw of the ROC curve is that it only provides ratios.
Okay.
At a given threshold, it might tell you your hit rate is 0.3 and your false alarm rate is 0.2, but ratios hide reality.
What do you mean?
Well, catching 1 out of 2 sick people is a 50% rate. Catching 1,000 out of 2,000 sick people is also a 50% rate. The ROC curve strips away the scale of your data.
Oh, I see. But the TOC reveals the total information in the contingency table, right?
Exactly. It shows you the actual absolute number of hits, misses, false alarms, and correct rejections for each threshold.
That seems much more practical. Another one the source mentions is the DET graph, the detection error trade-off.
Yes, this one plots the false negative rate against the false positive rate on nonlinear axes.
I love the analogy for this one. They deliberately warp the axis to spend more visual real estate on the errors.
Right. Stretching the axes solves a very practical visual problem. On a standard ROC curve, most of the graph is taken up by thresholds nobody cares about.
Yeah, and this relates perfectly to how the automatic speaker recognition community uses it. Like, if you're building Siri or Alexa, you're constantly balancing false alarms and missed detections.
Exactly.
If Siri goes off randomly during a quiet movie, it's highly annoying. But if Siri ignores your voice command when you're driving on the highway, it's actually dangerous.
Right. So the DET graph zooms in on the exact region of interest where those specific false alarms happen, rather than wasting space on the parts of the graph nobody cares about.
It's all about managing that annoyance to danger ratio.
Exactly.
Okay, there's one more alternative I want to hit. ZROC. Applying a standard Z-score to transform the curve into a straight line.
Yes. If we connect this to the bigger picture, this shows how different industries have had to customize how they measure truth based on what kinds of errors they can tolerate.
Right. And ZROC is heavily used in psychology, specifically memory strength theory tests.
Exactly. When you test memory, you're plotting the strength of recognition. And if you apply a standard Z-score, it transforms that bowed ROC curve into a straight line.
Which is so cool. The source goes deep into testing subjects with targets objects they actually studied, and lures objects designed to trick them.
Right. And this brings up the Yonelina's model of amnesia.
Oh, yeah, that blew my mind.
It suggests human memory is 2 separate mechanisms. First, you have familiarity, which is just a vague feeling. It operates like a continuous bell curve.
Okay.
Second, you have recollection, which is a discrete all-or-nothing process. You either objectively remember it or you don't.
And mathematically, adding that discrete recollection process bends the straight ZROC line, forcing it to become concave up.
Yes, but for patients suffering from amnesia who have lost that discrete recollection ability,
they only have the vague familiarity left.
Exactly. And because of that physical change in the brain, their ZROC curve loses its concavity and reverts to a straight line.
We are using a mathematical concept designed for WWII radar to literally map the geometric shape of human amnesia. That is just stunning.
It really is an incredible evolution of applied statistics.
So bringing it all back to you, the listener, whether you are reading a medical study, evaluating a business algorithm, or just reading a headline about a new AI.
You now know that accuracy isn't a single magical number.
Right. You are equipped to ask, where the threshold is actually set, and what kinds of false alarms are hiding under the curve.
Exactly. But we do want to leave you with one final provocative concept to mull over.
Oh, right.
Everything we've discussed today, yes or no, diseased or healthy, enemy plane or bird, has been about binary choices.
Right, two options.
But what happens when there are 3, 4, or 50 classes?
Oh, wow.
The source notes that to use RSC for multiple classes, you have to move beyond a 2D graph entirely. You have to calculate the volume under surface, the VUS, of a multidimensional hyperspace.
That sounds impossibly complicated.
It is. Imagine how exponentially complex defining truth becomes when we step out of a binary world and try to map out the infinite overlapping thresholds of reality.
That is a lot to think about. Next time I check my spam folder, I'm definitely going to be picturing a multidimensional hyperspace.
As you should.
Well, that wraps up our deep dive for today. Thanks for exploring the invisible math with us.